Good day, students. So we're continuing in the chapter 4 notes, picking up from the previous lecture. We said we'd come back to this example on page 12. So let's just recap briefly. So we've considered the definition of the derivative, and we've looked at finding the derivative from first principles. So to remind you that a derivative can be viewed as geometrically as the slope of the tangent line to a graph of a function, and also as a rate of change of one variable with respect to another. So we looked at the definition of the derivative here, evaluating the derivative at a fixed number a. And we also looked at allowing a to vary. So we find the derivative as a function of x. And on the right-hand side, this represents the slope of the tangent line at a point x. So that slope will obviously change depending on value of x that we are looking at. So we're coming back to this example here. We want to use the information in the graph that's given of f of x to sketch the derivative function. So at the outset, let me say that in order to sketch a unique graph of the derivative, we would need more information. So, but we can use certain pieces of information here to draw a possible derivative. So the first thing I'm going to highlight here is the values where the derivative is equal to 0. So that is where the slope of the function f of x is flat, horizontal tangents. So that's where the slope is equal to 0. So here we can put on the axis. So we know that if we're drawing the derivative function, it must cross the x-axis at these values where the derivative is 0. So I'll put some dots there to show that. Now we can put some tangent lines in as well. So I put some tangent lines in here. So you can see that here f of x is decreasing, f decreasing. In this portion. So that implies that the derivative then there in this section is less than 0. So in other words, it's below the x-axis. The derivative is negative. So when we draw the function, we must make sure that the derivative function, we must make sure that the y values are below the x-axis. And you can see that as I get closer to a, if I put another tangent in there, it's becoming less negative. So it will be negative and becoming less negative. Over here, if I put a tangent in between a and b, I can see that the function is increasing here, f increasing. And that then means that the derivative is positive. So it's positive, but it's becoming less positive. Okay, over here, between b and c, function is decreasing again. So that implies that f prime is less than 0. So it goes, the derivative function goes below the x-axis again after b and becoming less negative. So at some point it'll change. Sorry, not at some point it'll change. It will become less negative. Then at c it will cross the x-axis. Over here, f is increasing. So that means the derivative is positive. And it continues to be positive for the rest of the function. So if we put in a function, a derivative function now, we can see, okay, for values of x less than a, the derivative is negative and becoming less negative, and it must cross the x-axis at A. Okay, then between A and B, it becomes positive. And at some point, it's got to turn, still positive, but less positive, and meet back up with 0 at B. Then after B, the derivative becomes negative again, becomes negative, negative. And then at some point, it becomes less negative and must turn to cross the axis at C, and then continues to be positive. So that's a possible sketch of f prime of x. So when I said we would need more information, for example, we'd need more information to know what the y-intercept is. And of course, we don't know exactly where these turning points are for the derivative function. So we would need more information there in order to draw an exact graph of the derivative function. So just recall that that is not unique. And then I just wanted to come back to this example that we looked at in the previous lecture. The axis was incorrectly labeled here. It was labeled as minus 0.4, and this should be 1. But actually, that's not important. So please change that in your notes. That should be minus 1, because of course the derivative function here, f prime, is 3x squared minus 1, which means it has a y-intercept of minus 1. Okay, let's pick up then again on page 16. That's where we left off at the end of the last lecture. So we've discussed some alternative notations for the derivative. Let's just have another look at them. So we've got prime notation. So that's where we can say y prime or f prime of x. We've also got Leibniz notation where we say dy by dx. So that is the rate of change of y with respect to x, or df by dx, rate of change of df by dx. Leibniz notation. Sorry, that's a EI, not an IE. Leibniz notation. They're highlighted in turquoise. We can use a differential operator. So d by dx, I'm looking here at this one, d by dx of f of x, also d of f of x, and if we want to specify the variable, which we do if there's more than one, d subscript x of f of x. So just recall that we always say d, let me just label this rather, prime notation. And these are both examples of Leibniz notation. So recall that when we are using the derivative, we say d of something, df by dx. So if we just write d by dx on its own, we must have an of something here, because that is operating on some function. So we must either have an f or a y or something. D by dx on its own, if we just write d by dx, it means nothing. It's meaningless. Okay, we can also write that dy by dx is equal to the limit as delta x tends to 0 of delta y over delta x. So we distinguish between average, an average value, and that goes back to the discussion of the secant when we started off with the secant line. So delta y by delta x is the average rate of change of y with respect